So let's look at a hypothesis test for a mean, again using a t-distribution. Our t-statistic follows the same pattern that we saw for our test statistic in general of sample statistic minus null parameter divided by standard error. So if we now fill in the fact that I know my sample statistic when I'm working with one mean is always x bar, and my null parameter working with one mean is always mu naught, and my standard error I now have a formula for so that this standard error can be calculated. That then gets me to this combination of formulas here where we can calculate the standard error, put it into the denominator of the t-statistic, and the numerator will always be x bar minus mu naught. So let's put these formulas to use in an example. Looking at kitten weights, we're looking at the weights of 10 kittens born from a mother who tested positive for feline leukemia virus. And we are going to do some inference on this. Since we're given raw data and we don't know what our n, our x bar are just by looking at these data, we're going to have to go into StatKey and use descriptive statistics to calculate them. Since we don't have a data set for this, we'll have to enter the data manually. So coming over to StatKey, I know that I'm working with one quantitative variable. I'm going to come to descriptive statistics and graphs, and below that we have one quantitative variable, just like we did at the beginning of the semester. Coming here, I can then hit Edit Data, select everything that's there. Doing Control A is the quickest way to select everything, and then hit Delete, or you can manually select everything also. Now I'm going to type these numbers in, 99.8, hitting the Enter key between each. I always want to look at these two checked boxes here before I get out of this dialog box and think about them. First column is identifier. We don't have a first column. That would only be if you had like maybe a word, comma, and then the number. Data has a header row. That would be true if I had put at the top kitten weights and then started typing in numbers. If you just type numbers and nothing else, you can uncheck both of those boxes. And a good way to tell for sure that you chose the right settings is that your sample size is correct when you come out of the box. If I had accidentally left data has a header row checked, this would say a sample size of 9 because it would have assumed that my first entry was the header row. So I can see that I entered it correctly, and now this is giving me all of my summary statistics here, sample size, mean, and standard deviation. Right? I'm going to copy those over now. Another thing I'm going to do while I'm here is look at the shape. Now these dots are pretty spread out, so sometimes going to histogram is a little bit more clear. We can see that the shape we have here, we don't have extreme outliers, but there is a little bit of an outlier here at 110. So given that my sample size is just n equals 10, I'm going to make a note of that. The conditions aren't met as well as we might like them to be. So our conditions met for using a t-distribution for inference, we're going to say not necessarily, or maybe not. And we'll comment on the two things that we just noted. Here's how I will address this. We'll say that n equals 10 is fairly small compared to 30, and that observation of 112 is a bit of an outlier. It's not a really extreme outlier. If it were, we could say no, conditions definitely were not met. It's just a teeny bit of an outlier, so we will proceed with caution. So let's go ahead and state hypotheses. These are hypotheses for one mean, so they must be in terms of mu. My null hypothesis, let's go back and read the question again. According to the ASPA, kittens typically weigh approximately 100 grams at birth, and we're going to investigate whether average birth weight is lower among kittens born to a FeLV positive mother cat. So our null hypothesis is that the mean kitten weight, even to a FeLV mother cat, is still 100 grams, and our alternative hypothesis is that in fact it is lower. And now for our t-statistic, we get to use these formulas. First, we need to calculate the standard error. Standard error is the standard deviation divided by the square root of n. So that is 9.656 divided by the square root of 10. We then go into our t-statistic formula, which is x bar minus mu naught divided by the standard error. And my x bar is 92.510. That 0 isn't necessary for computations. My mu naught is 100. And my SE is 3.053. I get negative 2.453. All right, how many degrees of freedom are in the t-distribution? Remember that we use n minus 1 degrees of freedom. N in this case is 10. And therefore n minus 1 we're going to say is 9. All right, so let's go ahead and use StatKey to find the p-value for this statistic. We're also going to draw a picture of a t-distribution curve. We can do that part before we go to StatKey just to get a little bit of practice thinking about how big or small this tail should be. We have a bell-shaped curve here, centered at 0, and I'm going to mark my t-statistic of negative 2.453 out here a bit in the tail because it is greater than 2, but not extremely out in the tail because it's not much bigger than 2. So that's my t, and I'm going to color in just the left tail because of the fact that we are doing a left tail test. So remember to look at your alternative hypothesis to determine what tail it is you're doing or whether it's both tails. We need left tail only because this is a less than. This is not a two-tailed alternative hypothesis. So in StatKey we are going to go to t-distribution. And starting back over on the StatKey homepage, again, theoretical distributions. Now instead of normal, we skip to t. When I click on the t-distribution, it first asks me for degrees of freedom, and I'm going to enter 9. So now I'm going to select left tail and change the boundary value to the negative 2.453 that I got from my calculations. And hit OK, and it looks like we have a p-value here of 0.018. And we're ready to state a conclusion, a formal conclusion at the 5% level, since we were given a significance level on this one. We want to make sure that we're stating this just in terms of, is it statistically significant or not? We would in fact reject the null hypothesis at this level because 0.018 is smaller than 0.05. But our conclusion is all going to be in non-technical language. So I want to say, in the context of kitten weights, what we have statistically significant evidence of. So we have statistically significant evidence that mean birth weight of kittens born to a FeLV positive mother is lower than 100 grams, or we could say lower than the known average. By the way, these data are made up, so don't take this particular conclusion all that seriously. I do foster kittens, so I have kittens on my mind and in my house sometimes, and that's why I made up this example just so that we could have the cute picture of kittens here, right? All right, thanks.